So welcome to part 2 of the lecture on hemodynamics. If you've not watched part 1, then please watch that first. This will make far more sense that way. So we've talked about measurement of blood pressure, and now I'm going to talk about control of blood pressure. And I'm going to first focus on total peripheral resistance and arterial diameter. So we've already mentioned total peripheral resistance is set by the arterial system, but there are actually several factors involved with the control of blood pressure. That is the volume of blood, and we'll talk more about that in the next part of this lecture, part 3. There's the blood viscosity, because Purcell's law is related to the viscosity of the fluid. Now we can largely discount blood viscosity because it's more or less constant, as is often blood volume in the short term. So the two things that largely control moment-to-moment control of blood pressure, i.e. not long-term control of blood pressure, are the total cardiac output, and that's something I mentioned in lecture 2. It's the work done by a heart in a minute, and the resistance of the vascular system to blood pressure. And these things, while controlling moment-to-moment blood pressure, can also control blood pressure long-term as well. Now, I spent a while in part 1 of this lecture talking about total peripheral resistance, but I'm going to talk about it again because the mean blood pressure, as we've mentioned, is the cardiac output as a function of the total peripheral resistance. And total peripheral resistance is the sum of all the vascular resistances, i.e. the sum of the resistance to blood flow of the arteries, the capillaries, and the veins. Now, as I took pains to mention in part 1, it is the small arteries and arterioles, and I will just use the pen here, this section of the graph where we get control of total peripheral resistance, and that's because we have the largest site of pressure drop across the vascular system, and therefore we have changes in the diameter of these resistance size arteries, very small arteries, will determine or provide the most control over changes in the total peripheral resistance. And it's worth noting that these little arterioles are normally partially contracted. And as I mentioned in part 1, the resistance is dependent on the radius to the power of 4. So what that means is that small changes in radius equals large changes in the total peripheral resistance. And what we'll also see in part 3 is that the total peripheral resistance and the cardiac output actually affect each other. So let me just let me just delete this. So just to illustrate, because these resistance size arteries here are the normally partially constricted, what you can see is if they relaxed, we would have a reduction in overall blood pressure, and if they constrict, we have an overall increase in blood pressure. And it's worth bearing in mind that this pressure backfills as well. So if it goes up, because there's more resistance in the system, the overall blood pressure that we measure in the large arteries will be higher, and the contra is also true. So this is all occurring at the level of arterial diameter. And this is, an idea of the type of resistance artery we're looking at. only a couple of layers of smooth muscle cells, normally about the diameter of 2 or 3 human hairs. So if they contract and this lumen becomes much smaller inside, then we'll get an increase in resistance and we'll get an increase in total peripheral resistance and in the blood pressure. Similarly, if they dilate, we get a decrease in total peripheral resistance and therefore a reduction in blood pressure. Now, these arteries are normally partially contracted by the sympathetic nerves that are found within them, and I talked about this in the first lecture. So these sympathetic nerves almost universally release noradrenaline, and if you stimulate the sympathetic nerves, then stimulating them will reduce in contraction. Now, because these nerves are normally always partially active and the artery is partially contracted, if you reduce stimulation to these nerves, then you're removing vasoconstriction produced by noradrenaline and you would evoke some relaxation. The other factor that's involved here is these endothelial cells that line the lumen of the artery. They tend to release relaxing factors, and they tend to release relaxing factors into a response to increased flow through the artery and due to circulating hormones as well. So the arteries can constrict and relax via various mechanisms. I'm going to first deal with the endothelium dependent relaxation mechanisms. And what I'm showing you here is these are the endothelial cells shown in cartoon form. These are the smooth muscle cells forming the wall of the artery. And we'll cover a lot more of this information next year. So what's happening if there's flow, increased flow or shear stress across the endothelium, or if specific ligands or hormones activate receptors found on the surface of these endothelial cells, what they do is they increase a second messenger within the cells called calcium. And this increase in calcium stimulates this enzyme found within the endothelial cells. And that converts an amino acid called L-arginine into L-citrulline. And in this formation, it produces a gas called nitric oxide, or NO. And nitric oxide diffuses from the endothelial cell layer into the underlying smooth muscle cell layer, where it activates an enzyme which stimulates production of a second messenger called cyclic GMP, and this then causes relaxation of the smooth muscle and therefore vasodilation. And if you get vasodilation, you get a reduction in total peripheral resistance. So this is probably one of the most, this is the most common and probably most important vasodilator mechanism dependent on these endothelial cells. In fact, the discovery of this mechanism resulted in the award of a Nobel Prize. If we then look at the smooth muscle cells and think about contraction and relaxation in a bit more detail, and I'd like you to also refer to Professor Stevens' muscle lectures, where he'll also talk about contractile properties of muscle cells. Bearing in mind here we're talking about smooth muscle cells. Now, in the smooth muscle cell, when it's relaxed, it has a kind of elongated shape, and this elongated shape has filaments of the cytoskeleton running through it. So go back to my cells and environment lecture for more information about these filaments. And they're connected to dense bodies. These filaments are bundles of actin and bundles of myosin. When they contract, the smooth muscle cell bunches up. It shortens its length. Okay, and that's due to the actin and myosin sliding across each other. So the thick and the thin filaments within the cells sliding across each other. And myosin form the thick filaments and actin forms the thin filaments. Now, as I've already alluded to, that the process for this is a phosphorylation dependent contraction. So to activate the myosin, then what you need to do is activate myosin light chain kinase, and once it's phosphorylated, that then leads to constriction of the muscle fibers. So it's important to remember this process is phosphorylation dependent, but it is triggered by calcium. So calcium entry via voltage-gated calcium channels into the inside of a smooth muscle cell leads to activation of myosin light chain kinase and therefore constriction. And that's very different to the contractile mechanism of cardiac and skeletal muscle, where the contraction process itself is entirely dependent on calcium. And just to give a little bit more detail about how contraction can occur in vascular smooth muscle cells, here we have a receptor, a G protein coupled receptor, and you'll learn more about those in the future. Don't worry about this too much now. What I want to realize is there's an agonist binds to that receptor. That agonist causes a release of calcium from intracellular stores, such as the sarcoplasmic reticulum, and that binds to a molecule called calmodulin within the cell. This release of calcium from these intracellular stores also triggers entry of calcium from outside the cell through ion channels, and that calcium also binds to the calmodulin. Once this calcium is bound to calmodulin, it can then activate that enzyme we talked about, myosin light chain kinase. And once myosin light chain kinase is activated, it phosphorylates myosin light chain, and that is what causes constriction of the smooth muscle cell.